In this screencast, we're going to talk about a last major hypothesis test, two of them really, chi-square. So chi-square has two big uses. One is called one-way chi-square, or goodness, sometimes called goodness of fit, and the other is two-way chi-square, or independence. And this is only hypothesis testing. We're all done with confidence intervals. So let's look at an example to explain what one-way chi-square is. If you look at how blood type is distributed in the United States, so blood type is a categorical variable. People's blood type can be O, A, B, or AB. Those are categories, not numbers. And if you look at how those categories are distributed in the United States, we see this pie chart. 44% of people are type O, 42% are type A, 10% are type B, and 4% are type AB. So that's what the United States looks like. Now we're going to go to another country and ask, is that country's blood type distributed the same way? So in Norway, in a sample of 1,000 Norwegians, we find that 413 have type O blood, 480 have type A blood, 78 have type B blood, and 29 have type AB blood. So this is just a sample of 1,000 Norwegians. This pie chart is a reflection of the whole United States. This is a sample of just 1,000. And if we make a pie chart out of this sample, it looks like this. Well, it looks somewhat similar to the United States, but it's not the same. And so the purpose of the one-way chi-square test is to see whether Norway's blood type is distributed in that same split as the United States had. In Norway, is it true that 44% of people have type O, 42% type A, 10% type B, and 4% type AB? So in this second column here, this is what we're comparing things to because this is what it is in the United States. Here's what we actually found in Norway in terms of how many out of the 1,000. These are not percentages, these are the counts, the number of people. And then this Norwegian expected, this is how many we would expect to get if Norway did follow this 44, 42, 10, 4 distribution. So 44% of 1,000 is 440, 42% is 420, etc. So in this third column, we have what we actually saw in Norway, and in this fourth column, we have what we would expect to have if Norway followed the United States. And so what we're trying to, so they're not the same, but of course there's only a sample of 1,000 Norwegians, so we wouldn't expect it to be exactly that. Just like if you roll a die 60 times, you don't expect to get exactly 10 ones, 10 twos, 10 threes, 10 fours, 10 fives, 10 sixes. There's going to be some random variation. So the question is, are the differences between these two columns big enough to be statistically significant? And to test this, what's going on behind the scenes, we're going to just do it with Excel, but what's going on behind the scenes is we compute what's called a chi-square statistic. And the chi-square statistic looks at each of the expecteds, each of these observed, so these 413, 440, 480, 420, it looks at each of those pairs, see how far apart they are from each other, squares that, and divides by the expected, and then adds them all up. That's what this symbol means, adds them all up. And as you might expect, if the chi-square is really big, then you say, hey, Norway isn't like the United States. We're going to reject the null hypothesis. Now, we don't have to compute chi-square statistics or get our hands dirty. We're just going to use an Excel function, chi-square test. And I'll show you later in the screencast exactly how that works in Excel, but that's it. We're going to use the chi-square test, and it gives you a p-value. And so in our example, the p-value turns out to be 0.004, and we conclude that Norway is not like the United States. So a null hypothesis would be that in Norway, 44% of people have type O blood, 42% have type A, 10% have type B, and 4% type AB. The alternative is the blood types in Norway do not follow that distribution. So it's either they do or they don't. And if they don't, we're not saying exactly what's off, just that they don't follow that 44, 42, 10, 4 split. In this case, with the help of Excel, we get a p-value of 0.004. So we reject the null hypothesis. That means we've rejected that Norway does follow this and conclude that we have evidence that the blood type in Norway is not distributed as above. Why? Well, if Norway did have the above distribution, there would only be a 0.4% chance, that's the p-value, of finding a sample of 1,000 Norwegians distributed as far from the hypothesized as we did. So those 1,000 Norwegians that we got up here, could that happen if Norway looked like this? Yeah, it could happen that they'd be this far off, that the expecteds and the actuals would be this far off, but there'd only be a 0.4% chance of that happening, and so that's why we reject it. Okay, so that's a one-way chi-square. Like all of our tests, and we've underemphasized this in this class, but like everything we do, there has to be conditions to be satisfied before you can use these, or before they're statistically valid. And the conditions are that all the expected numbers have to be greater than 1, and 80% of the expecteds have to be greater than 5. So basically, this will ensure that you have a large enough sample size and you're not looking at things that are super, super rare. Okay, so now we're going to go into two-way chi-square. And it works similar, but it's a little more complicated. So two-way chi-square tests for relationship between two categorical variables. So is there a relationship between socioeconomic class and marriage status? Is there a relationship between religion and occupation? Relationship between general level of health and whether or not someone has exercised in the last month? And what would a relationship look like? What would that mean if there's a relationship between religion and occupation? Well, it might mean that people in one religion are more likely to be plumbers than people in another, or people in one religion are less likely to be doctors than people in another. So maybe Methodists are more likely to be carpenters than Mormons, or maybe Christians are more likely to be electricians than Muslims. Anything. So relationship could be anything. It just means that knowing something about one of the categorical variables tells you something about the other that you wouldn't ordinarily know. And we'll see examples. In fact, we'll see an example now. We're going to answer this question. Is there a relationship between someone's general level of health and whether they exercised, say, in the last month, because that's what our survey data is about. So let's see what this looks like. If you make a pie chart of all the people in our health data who have exercised in the last month and all the ones who haven't exercised in the last month, the pie chart for those who have exercised looks like this, the one on the left, and not exercised, the one on the right. And these pie charts are not the same. So that's what a relationship looks like. The pie charts are different. The distribution of the categorical variable health is different depending on which categorical variable or which value of the categorical variable exercise you have. And we talked about this in the earlier part of the course when we were talking about two-way tables and relationships between categorical variables, but now we're going to do a hypothesis test for it. These two pie charts are not the same. But remember, this is only a sample of 1,000 adults, some of whom had exercised and some hadn't. And so maybe that's just random chance. Maybe that's not reflective of what's going on nationwide. So the question is that difference in those pie charts small and due to random chance, or is it too large to be due to chance? And chi-square helps us answer this by giving us a p-value and letting us make a decision. So these are the raw numbers. 767 people in our sample had exercised in the last month. 233 had not exercised in the last month. Okay, fine. And if you remember, earlier in the course, we turned this into tables of percentages. Of those who had exercised, 26% were in excellent health. Those who had not exercised, only 19% were in excellent health. Of those who had exercised, only 2% were in poor health. For the non-exercisers, it was 7%. So earlier in the course, we looked at this table and said, oh yeah, there's a difference. So there'd be a relationship. But again, this is just a sample, and it doesn't make it very precise. How far apart do they have to be before we say there's something going on? And that's what chi-square does for us. So we turn this into a table of expected values, which we did earlier in the course. Remember where these numbers come from. This 184.85, the number of people we would expect to be in excellent health who had exercised comes from taking this row total, 767, times this column total, 241, and dividing by 1,000. These are what we would expect to see if there was no relationship between exercise and health. So if there were no relationship, we would expect to see these numbers down here. The numbers we actually saw are these numbers up here, and they're different. And we're just comparing these two rows to these two rows. This bottom one doesn't have a total row. The totals would actually be the same. So these numbers here are different from these numbers, top two rows here. And the question is, are they different enough to be statistically significant? Well, the p-value you get here is essentially 0. This is 10 to the negative 12. That's a decimal point, 11 zeros and a 1. It's 0. We reject the null hypothesis big time. There is a relationship between state of health and whether or not someone has exercised in the past month. Oops. So that would conclude our hypothesis test. We would go through the same 5 steps as we did before, but this gives us the p-value and we're ready to go. As a final note, let's just see how to use the function chi-square test in Excel. So let's get out of here and go to Excel. So here I put into Excel the table of observed values and expected values. And we were creating these tables earlier in the course. Remember, we get these expected numbers by row total times column total over grand total. And then the Excel function, we go to Formulas, More Functions, Statistical, chi-square.test. And what does it want? It wants to know where the actual numbers are, the observed, and where the expected is. So for the actual, we just highlight the actual numbers. Notice that we do not include totals here, just the data, just the counts. And the expecteds down here. Again, not the totals. And here we can see p-value. It's 1, actually 1.4, and this e negative 12, that's Excel's way of saying times 10 to the negative 12. It's a tiny, tiny number. It's like 1.5 out of a trillion. It's nothing. So there's just basically no chance this could happen if there was no relationship between health and whether or not someone had exercised. And for a one-way chi-square, it's just the same thing. We take, oops, not here, sorry. Let's just grab this and see how it works in Excel. So there's the actual, there's the expected. And we computed those expecteds just by taking the percentages times the 1,000 people we had. And let's copy this, put it in Excel. And then once again do chi-square test. So more functions, statistical, chi-square.test, actual, well, these were the actual 1,000 Norwegians. Expected, this is how many we'd expect if they followed that distribution. And there it is, 0.0004, almost no chance. And 0.0004, I'm thinking that I lost a 0 in my PowerPoint. Let's just go back and check. Yes, I did. So it's not just 0.4%, it's 0.04%. So that's even smaller. So, good thing to have checked. Yep. Okay, so that's how we do chi-square with Excel, and that's the concept of chi-square. You have categorical data, you look at what you observe, what you expected, and see how far apart they are. And that's the end.